we will start the discussion. Oxidation number and valency. Oxidation number and valency of the carbon atom is CH2, Cl2 respectively. How to calculate oxidation number? Molecule is CH2, Cl2. Structure is like this. Okay. So how to calculate the oxidation number of carbon? Initially, we can take already known oxidation numbers of atoms in a particular molecule. You know, without metal hydrides and H2, normally hydrogen takes +1 oxidation number. Here, +1 and again +1. +1 in 2 means +2. Okay? Chlorine is an electronegative atom. There are no any other electronegative atom. Therefore, chlorine can take -1 oxidation number. Okay, -1. There are 2 chlorine atoms. -1 in 2 is -2. +2, -2. Already, the charges are neutralized. Therefore, carbon should have 0th oxidation number. 0th oxidation number. And valency. What about the valency? For considering the valency, we have to think about outermost shell electrons. Okay, electrons of the outermost shell of carbon. So, what is the electronic configuration of carbon? 1s2 plus 2 to be 2. Okay, we have to consider the outermost shell. Then 2s2 and 2p2. Here 2 plus 2 means there are 4 electrons in its outermost electronic shell. Okay, 4 electrons are 4 electrons. 4 electrons are in its outermost shell. Okay, all 4 electrons you can see here is all 4 electrons are contributing to make bonds in CH2Cl2. Therefore, its valency is 4. Valency is 4 and oxidation number is 0. Answer is number 3. Okay. Increasing sequence of boiling points of compounds. When we are talking about the boiling points as well as melting points, we have to think about the intermolecular interactions or intermolecular forces between molecules. Okay, so now we have to consider the intermolecular interactions between each molecules. What are the compounds? First, CH2, CH3, CH2, CH2, CH3. Then CH3, CH2, CO, CH3. Then CH3, CH2, CH2, CH2OH. Again, CH3, CH2, CH2, C double OH. This is an alkane. This is a ketone. This is an alcohol. This is a carboxylic acid. Okay. To differentiate their intermolecular forces, initially we have to differentiate these molecules as polar and non-polar. So, what are the polar molecules here, and what are the non-polar molecules? You can see carboxylic acid is polar molecule. Alcohol also polar molecules. We should have polarity. Okay, polarity. And again, this is here like this now. This carbonyl group has a polarity due to the electronegativity of oxygen. It takes delta minus charge, and this carbon should has delta positive charge. Therefore, here also we can see a polarity. And this is a non-polar. Okay, all 3 are polar molecules. These all 3 are polar molecules. So, after finding their polarity or non-polarity, now we can compare their intermolecular interactions. So, how to classify their intermolecular interactions? Normally, non-polar molecules non-polar molecules have only van der Waals interactions or London forces or van der Waals interactions. But in these molecules, polar molecules, there is the intermolecular force we call it as bipolar interaction. Okay, bipolar interactions. Normally, these bipolar, so we have to consider same carbon, same number of carbon atoms here. In all four compounds, we can see only 4 carbons are there. Therefore, bipolar interactions are stronger than the van der Waals interactions. Therefore, these all 3 molecules should have the highest melting point or boiling point. That means the lowest boiling point or melting point relates to this one, alkane. Therefore, the sequence looks like this CH3. Okay, between these polar molecules, that means all have bipolar interactions. Between these, when we consider these bipolar interactions, there are normal bipolar interaction as well as there is a specific bipolar interaction that we call as hydrogen bonds. Okay. If some compound make hydrogen bonds, its boiling points and melting point get increased because hydrogen bonds are stronger than normal bipolar interactions. Okay, so initially we differentiated okay. Bipolar interactions are stronger than the van der Waals forces. Therefore, these all 3 compounds have higher melting points or lower melting points than this alkane. Therefore, the increasing sequence of melting or boiling points looks like this. Okay, this alkane has the lowest melting or boiling point. Then we have to consider these 3 molecules. Okay, initially, can you remember? Initially, we differentiate these molecules as polar and non-polar. That means we use the polarity. Okay, when their polarity is increased, their intermolecular interactions are highest. Okay, the strength of the intermolecular interactions are increased. Okay, when their polarity is increased, their strength of their intermolecular interactions are increased. That means their melting or boiling points are increased. Okay, according to that, among these 3 molecules, we can take the most polarized molecule. It should take the highest melting or boiling points. Okay, so molecules which can make hydrogen bonds have comparatively high melting or boiling points. Therefore, we have to differentiate these molecules who makes hydrogen bonds or who doesn't make hydrogen bonds. Okay, here ketone cannot make hydrogen bonds. For making hydrogen bonds, the hydrogen atom should be there. This hydrogen atom should make bonds with electronegative atoms. There are 3 electronegative atoms we are talking about: nitrogen, oxygen, and fluorine. Okay, when hydrogen is made bonds with fluorine, oxygen, or nitrogen, this particular molecule can make hydrogen bonds between same molecules as well as another foreign molecules. Foreign molecules should have these types of bonds. Okay. Example: H2O. 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 Okay. Then due to the polarity, oxygen takes delta minus charge and hydrogen takes a delta plus. Again, delta plus and delta minus. Okay. With these two polarities, there is a hydrogen bond. Okay. Now you can see hydrogen can make hydrogen bonds with their own molecules, same molecules, as well as when some molecule has hydrogen bonds, another molecule like CH3OH, H4, CH3. Okay, due to this polarity, oxygen takes minus delta minus and delta plus. Okay, between here delta plus, delta minus. Okay, between these two, hydrogen and oxygen, there is a hydrogen bond. Okay, therefore, water can make hydrogen bonds between same molecules, their own molecule, as well as foreign molecules, which can make hydrogen bonds. Therefore, you can see ketone cannot make hydrogen bonds because oxygen here, CO means there is a carbonyl group. Oxygen is bound with carbon, not hydrogen. Hydrogen, here you can see hydrogen has been made hydrogen bonds. Therefore, this ketone has normal bipolar interactions. Here, hydrogen and oxygen, there is the OH bond. See, double OH means this one. Okay. Here you can see there is hydrogen bond. Therefore, ketone, the next molecule is ketone because it cannot make hydrogen bonds. Its intermolecular force is lower than the alcohol and carboxylic acid. Therefore, melting and boiling point of ketones are lower than alcohols and carboxylic acid. Therefore, the next molecule should ketone CH3, CH2, CO, CH3. Between these two molecules, initially you can remember we differentiate these molecules according to their polarity. Okay, at the final stage, we have to consider about its polarity too. So, how to differentiate these two molecules, polarities of these two molecules? Here you can see what about the polarity of this OH bond. This OH bond. Here you can see actually no effect on carbon, hydrogen. You can see no effect on the oxygen atom from carbon atom because hydrogens are electropositive atoms. They pull electrons towards the carbon. Therefore, no need electrons from oxygen to this carbon. Okay, so oxygen is in a free situation, but in here, okay, when we consider this OH bond, polarity of this OH bond, here you can see due to the electronegativity of this oxygen atom, okay, it pulls electrons from the carbon. Therefore, there is an electron deficiency. That means positively charged is there. Due to this positively charged, carbon tend to pull electron from this oxygen. Therefore, this polarity gets increased than this one. Okay, highest polarity is there. Therefore, the highest intermolecular interactions are there. Therefore, the highest melting or boiling points are there. Okay. The next molecule is CH3, CH2, CH2OH, then CH3, CH2, CH2, CH2H. Answer is number 1. Okay. An element shows only 2 and 4 valences. We have to find the correct electronic configuration. Okay. If you can identify each atom, each element with a two electronic configuration, you can easily catch the answer. 3D4, 4s2 means chromium. And 2s2, 2p, 4 means oxygen. 2s2, 2p, 2 means carbon. 2s2, 3p, 4 means sulfur. 3s2, 3p, 1 means aluminium. Only 2 and 4 balances carbon. Okay. Only 2 and 4 balances show carbon. Here 1 is 2, 2 is 2, 2 is 2. So balance is 2 and 4. Answer is 2 carbon. Compound with the highest bipolar movement. So we have to compare each bipolar movements of each compounds. First one, chlorine, hydrogen, chlorine. Then chlorine, chlorine, hydrogen, hydrogen. 4 chlorines are there. Then chlorine, chlorine, bromine, bromine. Here you can see chlorine, chlorine, bromine, bromine. Okay, how to compare each bipolar movement. Here you can see two electronegative atoms. 2 chlorine atoms are pulling electrons from carbon in this way and this way. Therefore, the overall or the net attraction goes to this direction. Here, hydrogen pulls electrons now. Therefore, the overall direction is here. So, this is the overall direction. Here, there is bipolar movement in this direction. Here, 2 chlorines, same elements are pulling electrons from opposite direction. Same force of opposite direction means the force is cancelled. Here again, same force into opposite directions. Therefore, bipolar movement, overall bipolar movement is 0. Okay. 4 chlorine atoms pulls electrons into 4 directions. Again, it should 0. And here you can see 2 chlorines are pulls electrons into this way and this way. Overall goes to this way. Bromine is somewhat electronegative atom. Therefore, there is force downward. But when we consider these two forces, the overall direction is this one. Okay, overall goes to this one because electronegativity of chlorine is higher than the bromine. But here the bipolar movement is not much as this. Okay, up to now the highest bipolar movement is this. Here again, same elements pulls electrons to same directions. Overall 0. Answer is number 1. Mass of K2SO4 Cr2 SO3 twice 24H2O. Okay. Compound is K2SO4 dot Cr2 SO3 twice 24H2O. We have to find the mass of this compound for make it Cr3 plus ions. The concentration should be 10.2 and 1.00 cubic decimeters. Imagine the whole system, the whole container, so the volume of the whole container is about 1.00 cubic decimeter. Then you can easily solve the question, solve the problem. Okay. So overall, system is about 1.00 cubic decimeter. So we have to make Cr3 plus ions 10.4 ppm. Initially, we have to convert this concentration into non-concentration. So 1 ppm equals to 1 ppm minus 3. No? Therefore, 10.4 is equal to 10.4 is equal to 10.4 mgpm minus 3. Then we can convert this mgpm minus 3 into grams. Okay. For converting the milligram into gram, we have to multiply the value by 10 to the power minus 3. Then 10 to the power minus 3. This is the mass of chromium ions in grams. Okay, ions in grams. Then we can calculate the moles of Cr3 plus ions for making 1.00 cubic decimeter. Then calculating the number of moles of Cr3 plus ions, we have to divide the mass by its smaller mass, it is 52. Then we have calculated number of moles of Cr3 plus ions. Okay. Now we have to compare the number of moles of the chromium P plus ions with this one. And after calculating the number of moles of whole compound, we can calculate the mass. Okay. Initially, we have calculated the Cr3 plus moles. You can see in 1 mole of compound there are 2 moles of chromium ions. That means for making 1 chromium mole, okay, for making 1 chromium mole, half of the whole compound is enough. Therefore, if the total chromium moles are there, whole compound, the moles of whole compound should be half of the chromium 3 plus ions. Okay. Therefore, now we have calculated the number of moles of whole compound. Okay. And if its molar mass is given 894 gram per mole, then after finding a number of moles, according to this equation, this relationship, this is the mass, this is number of moles. So we have to calculate mass. Okay. Therefore, the number of moles should multiply by mole mass. Okay. Then we can calculate the number of mass in mass of small compound in grams. Okay. After calculating, you can see 52 into 2 means 104. Okay. 10.4 and 104. There is a 0, 0.1. 0.1 and 10 to the power minus 3 means 10 to the power minus 4. Answer should be 894 into 10 to the power minus 4. That means 0.0894 grams. Are there any answers? No. But we can convert this into kilograms. That means we can multiply this value by 10 to the power 3. Then 1, 2, 3. 89.4 milligram. There is an answer. Answer number 5. The element should be presented here. The element should be presented in D block. Okay. You can read the question. I'm explaining now. The element should be presented in D block as well as it is not esoteric element. Most of the esoteric elements are in the block. Actually, most of the elements of D block are esoteric. You know, what are the 10 elements of D block? 3D: scandium, titanium, vanadium, chromium, manganese, ferric, cobalt, nickel, copper, zinc. Okay, D1, D2, D3, D4, D5, D6, D7, D9, D10. Okay, now the particular compound should be included into the D block and it should not esoteric. For considering esoteric element, particular element should be included into the D block is the initial condition. The second condition is the particular element should have partially filled the sub-energy level in its elemental stage or most stable positive ionic stage. Okay. Initially it should be included in the D block. Okay. Should be included into the D block for considering as an esoteric element, and in the elemental stage, it should have partially filled these sub-energy levels. Okay, if not, then we can go to the second step. Then we can search, are there any partially filled D sub-energy level? Are there any partially filled D sub-energy levels in the most stable positive ionic stage? Okay. These all elements fulfill this condition. Therefore, no doubts. You can write the electronic configuration of the elements, and we have to compare scandium and zinc. Scandium and zinc. Scandium in the elemental stage, its electronic configuration is 3.4s2. Therefore, it has partially filled D difference, the sub-energy levels in the elemental stage. But zinc, you can see it is 3D10-4s2. Okay, and we have to work. We have to move on the next condition. We have to move on to the next condition. The most stable positive ionic state should have partially filled D sub-energy levels. The most stable ionic species is zinc 2 plus. Now, zinc 2 plus means its outermost 4 electrons are removed. That means here electronic configuration is 3D10. But here also we cannot see partially filled D sub-energy levels. The 3D sub-energy level is fully filled. Therefore, answer is zinc. Zinc. Okay. Zinc is included into the D block, but is not considered as an esoteric element. Here, we have to have an idea about the shapes of these molecules. CO2 and PeCl2. CO2, PeCl2. You can see both have linear shape and no same shapes are there. Second one, PO4 3 minus and S2O3 2 minus. PO4 3 minus tetrahedral shape. S2O3 also has a tetrahedral shape, central atom sulfur, and again sulfur atom, oxygen atom, oxygens. Okay. Again it is tetrahedral. NCl3 and BCl3. NCl3 is pyramidal shape due to this lone class of electrons is pyramidal. And BCl3 is trigonal band. Okay, there is an electrodeficiency. Boron, this is the central atom, boron. Here, the shape is trigonal band. And NO3 minus and SO3. NO3 minus. NO3 minus. Like this one. NO3 minus. And SO3 also have trigonal, both have trigonal band. Therefore, answer should be this one, NCl and NCl3 and BCl3. Two different shapes are there.